Hello, my name is Gotin Adjovu. I'm a PhD student at the Department of Civil and Environmental Engineering and Construction here in UNLV. I work with Dr. Sajad Aman and Dr. Harun Stephen. Today I'm presenting on utilization of remote sensing techniques for the estimation of total dissolved solids in water bodies. In this presentation, I'll be giving the background, talk about the objective. I will also talk about the study area, present the approaches and the methodology used. I'll talk about the results and discussions. I will give some summary and then end with some references used. The knowledge of water quality parameters and its characterization is key in order to protect and restore the quality of water resources. Water quality parameters are characterized as physical, chemical, and bacteriological parameters. Some of the physical parameters include dissolved oxygen, total suspended sediment, electrical conductivity, and total dissolved solids, which is also known as salinity, which this study focuses on. Monitoring of water quality parameters have been traditionally carried out through field and lab work. These approaches are costly, labor-intensive, and time-exhausting. Remote sensing, however, offers an alternative approach. Remote sensing techniques allow for analysis of these water quality parameters on large scale, and they are not limited to a single location in space and time. They offer an effective tool for monitoring. Several of remote sensing sensors have been used in various studies, including Landsat 5, 7, and 8 sensors, and the Advanced Spaceborne Thermal Emission and Reflection Radiometer, which is ASTA. These sensors have been used in the determination of TDS, TSS, chlorophyll concentration, turbidity, algae content, total dissolved organic matter, and so on. This research, however, focused on the estimation of TDS on the Colorado River using Landsat 8 operational land imager, which is known as Landsat 8 OLI. Salinity in the Colorado River is an issue of concern because it causes the US government a sum of almost $400 million in economic damages yearly. TDS also leads to the limitation of biodiversity, shortening the lifespan of aquatic species in the water. The US and the Republic of Mexico signed a treaty in 1944 which limits the TDS concentration in the water that is discharged to the Republic of Mexico. Hence the need to critically look into this water quality parameter. The research focused on establishing a relationship between spectral reflectance on Landsat 8 OLI images and TDS concentration in a river system in the US, here with a more focus on the Colorado River. The Colorado River has a length of about 1450 miles and then a width of 200 to 2500 feet. The river basin is largely an arid to semi-arid region with a precipitation of 4 to 60 inches yearly. The Colorado River Basin houses several reservoirs including Lake Mead and Lake Powell, which are facing drought. The Colorado River and its tributaries provide water to approximately 36 million people and irrigate 5.5 million acres of land in the western US, including Nevada. It also provides water to approximately 3.3 million people and irrigate 500,000 acres of farmland in the Republic of Mexico. The study area is, as I mentioned, is the Colorado River. This is a Colorado River passing through several states. We have California, Nevada, Arizona. So these are currently some USGS stations, United States Geological Survey stations on the Colorado River, which measures electrical conductance. Out of these electrical conductance, TDS is computed, and this TDS will now serve us as a ground truth or field data to be used in analysis. So here the study of interest is located above the Imperial Dam of the Colorado River. So this is the station of interest, and then it's located around the Arizona-California boundary. So in this presentation, the approach includes data collection, and of course the data include Landsat images, which is Landsat 8 OLI, and then the ground truth data, which is the TDS data I spoke about. So once we have the satellite data, we have to correct for atmospheric effects. So correct using what we call the dark object subtraction method, and then this is how it works. So as the solar radiation travels through space and enters the Earth's atmosphere, it kind of strike particles in the atmosphere and then reflect back the particles to the sensor. So this erroneously increases the radiance values, hence the need to correct. So when we are correcting, we assume 1% because the fact that the target portions of the Earth's surface are absolutely black, and then there are very few of this, and 1% is assumed to be good assumption as opposed to assuming 0. So here, as we have the dark object corrections or dark object subtraction method applied, then we have the corrected reflectance. Once that is done, then we kind of compute the indices, which are salinity index, which is just a combination of the bands, and then we have a model being developed. Once the model being developed with the ground truth data and these indices, then we can do some statistical analysis to see the predictive power of the model, and then we map the water quality parameter here, TDS, in the river. So the Landsat 8 welleye data was retrieved from the USGS data repository with this link. So this Landsat 8 has different bands ranging from band 1 to band 10 to band 9, so each with a special resolutions. These are free and open access data with a repeat cycle of 16 days. What it means is that you can get this data every 16 days. So the downside of this, unlike lab or field method, which you just go to the river, get your sample and do your analysis as to when you want, this one you have to wait to 16 days before you get the data, and that's the downside. But as this data is free and open source, so it also provides us to save money. So the USGS has field measurement of TDS data, as I showed in the previous slides. So out of this electrical conductors, we have the TDS data. So for the purpose of this study, focus on the station which is located above the Imperial Dam, as I mentioned, and then we have a data on TDS for 2018. So here is the ranges of TDS and then discharge, which is the flow. So we can see that the TDS from the beginning of the year starts rising, and then it starts reducing as it gets almost to summertime, and then it reduces. So the reason for this reduction is something that this study also hopes to look at. And then we have the flow ranging from keeping almost constant, about 8,000 to 10,000 cubic feet per second. So these are the bands that I mentioned. So the Landsat 8 welleye has different bands. So here are bands of focus are band 2, 3, 4, and 5, and these are the name of the band with their wavelength and their resolutions. So once we are able to do all this correction, we get reflectance in this band 2, 3, 4, and 5, and then the combination of the bands. So for salinity index 1, we have it being the square root of the reflectance in the red multiplied by the reflectance in the blue bands. So that is salinity index 1. For salinity index 5 is just the reflectance in the green band multiplied by the reflectance in the red band. So all the other equations apply. So here is the result. So this is a coefficient of determination R square using a linear and polynomial fit. So for band 2, other bands are left out because these are the bands that are getting good results. Band 2, 3, S1, which is salinity index 1, 2, and 5. So here we can see that salinity index 5 is giving us pretty much greater results in terms of polynomial fit. We're having about 84% prediction, which is very good. So R square we obtained for B2, B3, S1, S2, and S5. And this result kind of confirm previously done work in close to this area, or close to this topic actually. So we have band 2 and band 5 being the most suitable method for detection of TDS. So further analysis proved that so this is the results from band 2, the graphical representation of that, and then we have that of band 5. So further indications indicate that band 5 is giving us good prediction, about 84% in terms of polynomial fit. So from that, the univariate model that was adopted is y is giving us this value, which is 0.00005 x squared minus 0.0165 s plus 5.055. So what this means is that we have the y being the satellite salinity index 5, and then x being the total dissolved solid. So for a given year, let's say 2019, 2020, when you collect these Landsat images, you can compute the salinity index 5 using the relation given, and once you have the salinity index 5 for all the for the data given, then you plot, then you are able to predict the total dissolved solids without carrying out any field or lab analysis, which saves a lot of money. You are able to know the same information you would have carried out using field or lab work, which are expensive. So in summary, remote sensing provides cost-effective approach for the estimation of water quality parameters, and then the study developed a univariate model. Here we have polynomial model for TDS prediction, and sensitivity analysis needs to be carried out on this to check for the predictive power of this model. Other models could also be utilized in future, which include artificial neural network and support vector machine systems. So established model could be used for estimation and mapping of water quality parameters. So here are some of the references that have been used. And then if you have any questions, thank you very much for your time. If you have any questions, please send them to my email and I'll be happy to respond. Thank you.